Lesson 2.2, the factor theorem. The factor theorem works hand in hand with the remainder theorem. So in the remainder theorem, you took a binomial, divided a polynomial by that binomial, and you got a remainder. But then we figured out that in order to determine what the remainder would be of dividing a polynomial by x minus b, all we had to do, here's our polynomial, all we had to do was find out what p of b is. And whatever that is, that's the remainder for if we had divided out this whole thing and gotten a remainder down at the end of our long division. Okay. Today we're going to talk about the factor theorem, which is the really just a helpful application of the remainder theorem. And basically it is to find factors. We need to find a value of x such that the value of the polynomial at that point is 0. So we want to sub in p of b and get 0, and then we know that we found a factor. So we'll write that in words that we can hopefully understand. Factor theorem says this: x minus b is a factor of p of x. Okay, that's just any polynomial. If you're not sure what that is, then write the word polynomial in front of it. X minus b is a factor of polynomial p of x if and only if p of b equals 0. Okay? So if the value of the function at b is 0, then we know that x minus b is a factor. Okay, that's in its simplest form, but we also know we deal with binomials that don't have 1 as the coefficient of the x term. So we need a second note for that. We need the binomial ax minus b. And we're going to write the same sentence. Is a factor of polynomial p of x if and only if, and you can probably guess what the fill in the blank is here, p of b over a is equal to 0. Okay, these statements come derived directly from the remainder theorem, and our goal today is to apply them and to see how they work and to get good at using them. What is the point of this? Why is it so helpful? Well, a little note underneath. With the factor theorem.
Why is it like that though? Like that's really confusing.
Here, one sec. Let us finish taking this note, and then we can talk about it a little further.
Okay.
With the factor theorem, you can determine the factors of a polynomial. You can determine the factors of a polynomial without having to divide. Without having to divide. Okay, the question comes, Mr. V, put this in context. Why does this work? How does it work? Okay, let's say you had a polynomial. Let's say we had p of x, and let's say it equals, I'm just going to pick a fairly simple one, x squared plus 5x plus 4. Okay? And we kind of know that's a quadratic, and we can factor that fairly easily. Well, what is the point of factoring this quadratic? Okay, I know it factors into x plus 4, x plus 1, because I need two numbers that add to 5 and multiply to 4. Okay, so I know this is the factors. What does that tell me? It tells us exactly where the zeros are. Okay, so basically what it says is that if you were to put a 4, a negative 4, into this equation for x, you would find a 0. What does that mean? Well, it's where the value of the function, you can write the value of the function, p of x, it's where that is 0. So x plus 4 is a factor, x equals negative 4 is a 0. So the connection, it's called a 0 because it is where, if you put x equals -4 into the function, -4 squared plus 5 times -4 plus 4, you would get 0 out the other end. So it tells us where that x-intercept is over here at -4, which tells us that it's going to make this whole equation equal 0. So there's a direct connection between, well, I mean, it's the same thing. It's basically just graphing a 0. Tells us that the value of the function at this point is 0. And we know already that it is a factor of that equation. So it's a connection between the factors and the x-intercepts. If we took the value of, x equals 0, and we said, well, sub that in, well, the value of the function at that point would not be 0. 0 squared is 0 plus 0 plus 4. You'd have, at x equals 0, you have a y value of your polynomial function up at plus 4. So that is not a 0. Therefore, x by itself is not a factor of the polynomial. And you can do that for any number. Let's say you have x minus 2, and you want to test if that is a factor. Well, you sub in p of 2. Okay, you get 4 plus 10 plus 4, that's 18. So the value of the function at x equals 2 is actually way up here at 18. Okay, so it's clearly not a 0, and x minus 2 then is not a factor because our factors indicate our zeros. Does that make sense?
Yep.
So that's the connection kind of broken down. We're going to see that as we work through some problems. We're going to jump right into example 1. In example 1, it asks, which binomials are factors of the polynomial 2x cubed plus 3x squared minus 3x minus 2? Okay, which binomials? So we're going to get a list of binomials and we're going to test them according to this factor theorem. So all we need to remember is that x minus b is a factor if and only if p of b is 0. And likewise for ax minus b. That's what we're keeping in mind as we work through.
That would be like mathematically.
Okay, so in example 1ai, we are going to test whether or not x minus 2 is a factor of p of x, which I'm just going to jot down for myself. 2x cubed plus 3x squared minus 3x minus 2. Always make sure you've copied things down properly. And in order to test whether or not this is a factor, I do not have to divide the polynomial by the binomial. Instead, all I have to do is here x equals 2, okay, would be the corresponding 0, okay? So all I'm going to do is sub x equals 2 into p of x. Okay, so here we go. I'm finding p of 2. So anywhere I see an x, I'm going to put a 2. I'm going to work that out. Using BEDMAS, order of operations, I've got 8 times 2 is 16, plus 4 times 3 is 12, minus 6 minus 2. Okay, so now I have 28 minus 8, that's 20. Now, the value of the function when x equals 2 is 20. So it's not a root, not a 0, not an x-intercept. Therefore, x minus 2 is not a factor.
Crazy idea. What if we
So the question comes, why can't we just factor it out as a cubic? Right now, we don't have the skills to factor cubics. In order to factor this all the way, you need to start with one of its factors. In this case, we're testing to find that first factor. We now know that x minus 2 is not a factor because p of 2 is not 0. But as soon as we find that first factor, then we can use our skills to divide this out by that factor. It'll leave us with a quadratic, and we know how to factor quadratics without this method. So the only thing you know how to factor right now is a quadratic, okay? When it's given in this form, at least. Okay, let's test a couple other factors here. We might not do all of them, but we're going to test the factor of x plus 2. Now keep in mind, the theorem, the original statement is x minus b. So in this case, what is the value of x? If you have x plus 2, then the value of x is negative 2. Okay? Basically, you're looking for the x value that would cause this to be 0. Yeah? It's x equals b, and it's x minus b, so it's negative 2. Sub x equals negative 2 into...
I found out that if you sub in 1, it's 0.
Sounds good. So we've got x equals minus 2. We're going to put that in there. What do we end up with? We end up with 2 times negative 2 cubed plus 3 times negative 2 squared minus 3 times negative 2 minus 2. We've got negative 8 times 2 is negative 16. We've got positive 4 times 3 is positive 12. We have positive 6 minus 2. Ooh, my negatives here, I have 18 negatives and I have 18 positives. This is 0. Therefore, x plus 2 is a factor of p of x. So now if you wanted to factor out the whole thing, all you would do is go x plus 2, and you'd put p of x on this side. We're not going to do it, I'm just explaining it to you. You would perform the long division. You would end up with a quadratic here, which you could then factor out into its two factors. The first factor being x plus 2, the other two binomial factors coming from the quadratic that remains after you factored that out. Okay? If this p of x was an even longer polynomial, it was, say, to the power of 4 or to the power of 5, you could perform this step multiple times in order to get the first couple of factors. Once you're down to a quadratic, you know how to factor that using sum and difference or factoring by grouping. Okay? Sorry, sum and product and factoring by grouping. Here we are just asked to continually test each factor that they're giving us. So in subsection 3 here, and I'm not going to do it every time. This time I'm just going to give the answer. So we're asked to test if x plus 1 is a factor. So what do? You sub in negative 1 for x. And if we were to do all of this, we would find out that that equals 2. Therefore, not a factor.
If you do if you sub in p1 for x, or no, yeah, you end up just getting 2 plus 3, subtract 3, subtract 2.
Yep. So that's our next factor that we're testing, x minus 1. What would you do? You would sub in 1 for x. You'd find out that it does equal 0, as if you do the arithmetic that we did in our first two. Okay? Therefore, x minus 1 is a factor. Let's go to our fifth one. The fifth one is 2x plus 1 is the factor that we're testing. Now we're applying the second statement in the factor theorem, which says that 2x plus 1 is a factor of the polynomial p of x if and only if p of b over a. And remember here, it's ax minus b. So this value is negative 1. So what we're looking for is p of negative 1 over 2. We learn that if we were to sub that in for x in our polynomial, that does equal 0. Therefore, 2x plus 1 is a factor. Okay, now if we look to part B, it says, okay, so take your p of x, which I rewrote right there, and write it in factored form. Basically just use the factors that you found out that are legitimate factors and write this thing in factored form. And we can double check that we have them all because this is a cubic. And we have a factor here with an x. We have a factor here with an x. And we have a factor of x here. So that's all three of them because we can account for x to the power of 3. So here we have it. P of x equals x plus 2, x minus 1, 2x plus 1 in factored form. So again, in this case, we were asked to test a whole bunch of factors, and we found the 3 that are actually factors using the factor theorem. When you're doing this for practice problems and things like that, you'll actually just do this test until you find one that is a factor. So that's not a factor, this is a factor, and then you'll use long division to find the other 2 factors, okay? You won't keep on testing test values. It's just in this case, they gave us the factors to test and asked us to do that. So it's just practice using that theorem. Any questions there? This is how example 1 ended off. We could express our given polynomial, p of x, in factored form. And what I want you to look at is consider the factors that we ended up testing. Okay, so this is 3 of the factors that we tested. Okay, the other 2 I'm not going to write down, but let's look at the ones that we actually ended up using. Is there any relationship between the zeros, the factors of p of x, and the constant term of p of x? What is the relationship between the factors and the constant term? Any relationship between these 3 factors together and the constant term? Product of the constants within each factor. Okay, so we have 2 times -1 times 1 ends up being -2. So what does that tell us? Well, if we're testing p of b, that tells us that in this case, the only values of b that need to be tested or is even useful to test are actually +1, -1, +2, and -2, because those are the only values that will generate factors that contribute to a constant of -2. If you were to test a value, if you were to test b equals 3, it will never be result in 0. It will never tell you that x minus 3 or x plus 3 is a factor. It won't work out. There will always be a remainder, because if a 3 here, you could never generate a 2 there.
You're probably never going to give us decimals, right? We're always working with full numbers.
You could potentially, yeah, in the constant, in the polynomial that we give, no, you won't have a factor. If you do, you could multiply every single term by the denominator, and then you'd get whole numbers. Yeah, okay. That would be really ruthless, because in the case where you're working with p of b over a, then you'd have a fraction over a fraction, which would be just pretty convoluted. But the same principle applies for finding out what value of a is going here. We can look at the leading coefficient and say, well, the only factors that could divide this thing out could have an a of 1 or an a of 2. I wouldn't ever bother testing a equals 3 or a equals -3, because there's no way that a factor with a coefficient of 3 in front of the x could ever multiply out and have a leading coefficient of 2. 3 times 1 is already 3. So the highest number that could possibly be the value of a in any of my factors is 2 or -2. Okay, so we've established the things that we're not going to test because they can't be. So now let's talk about what could be. Okay, we're going to consider a different polynomial, and on the top of page 12 in your notes, we're going to take a few notes here, okay? We're going to consider consider p of x, the polynomial p of x, and let's say it equals x cubed plus 2x squared minus 5x minus 6. Okay? Now, we could rewrite this. Let's not. I'm not going to rewrite this thing. Basically, what we're going to test as values of b, that so in ax in the factor x minus b, b must be a factor of -6. Okay? It must be, and we talked about that already. So all that we're going to do when we're testing values of b is we're going to test factors of -6, because the constant term in each binomial is going to be multiplied together by the other constant terms. It's going to result in -6. So the constants in each binomial have to be factors of -6. So we would test values of b. Test values of b are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Those are the only things that it can be. Okay? That gets us into the definition for the integral zero theorem. Okay? It's called the integral zero theorem. The zero theorem is going to help us to find the zeros. Okay? And integral is, the base word is integer. So these are the whole numbers that can be used to find factors of this polynomial. Okay, the whole number values of b. Next, we're going to get into the rational zero theorem, which you would use if there was an a value here that wasn't 1. But we'll get into that when we get there. So here we're just going to write this down. The integral zero theorem states if x minus b is a factor of polynomial p of x with leading coefficient 1, so p of x has a leading coefficient of 1, and so does our factor x minus b, and p of x has and remaining coefficients that are integers. So take, for example, the p of x that we have here. The next coefficient is not 1, but it is an integer. Minus -5 is not 1, but it is an integer. Okay? It doesn't work if they're decimals or fractions. But if the leading coefficient is 1 and the rest of the coefficient are integers, then b is a factor of the constant term of p of x. Okay? So let's see what that looks like. Now we are able to determine which values of b I actually want to test when I'm trying to find factors. Okay, so in example 2, we have the instruction to factor x cubed plus 2x squared minus 5x minus 6 fully. but they're not giving us any of the factors to start with. We have to find our own factor to start with, okay? So what we're going to do is we are going to find a value of b such that p of b equals 0. That's our goal, right? If the remainder is 0, then x minus b is a factor. And now we know which things to test. We're going to test factors of -6. That's what our integral 0 theorem says. Okay? It says that b needs to be a factor of the constant term of p of x. So test factors of -6. We're going to test for b. We're going to test plus or minus 1, plus or minus 2, plus or minus 3, and plus 6, -6. Okay, those are all the factors of -6. Okay, so let's start from the easiest one, right? The easiest thing to find out is we are going to sub x equals 1 into p of x and see what that looks like, okay? So p of 1 is, I'll write it out for the first one, but after this I'll probably do most of them in our heads. But anywhere I see an x, we're going to sub in the digit 1. So we've got 1 cubed, that's 1. We've got 1 squared times 2, that's 2. We've got -5 minus 6, that is not 0, okay? So once I'm doing this in my practice problems and I know it's not 0, I'm just going to go not 0. Yeah, this not equal to 0. Then I'm done. I don't have to think about it anymore. It's obviously not 0. For the sake of this practice problem, I'll go that's 3, take away 11, that's -8, which clearly isn't 0. Which value would we like to test next? Well, you can either work for positive numbers, like you can, yeah, you could try -1, or you could sub in x, yeah, or you could sub in x equals 2. I'm going to do x equals 2 because I know it gets us to an answer faster. Although -1 could be 1 too, I haven't checked. But anyway, I know that this one's going to work. So we sub in 2 anywhere we see x. That gives us 2 cubed, which is 8. It gives us 2 squared times 2, which is 8. It gives us 2 times -5, which is -10, and our constant -6, and that equals 0. Then we can say, therefore, x minus 2 is a factor. Okay, once, and we're going to make a note of this, once one factor is determined, once one factor is determined, use other methods to find other factors. Basically what we're saying is we're not going to keep testing these values. If it was a quartic or a quintic, then we might have to do this step all over again. But first we would have to divide it by x minus 2. Well, we wouldn't have to do this first, but it's easiest if you divide it by x minus 2 first, get a new factor, a new polynomial, and then go from there. Okay?
-3 and -1 are both zeros. So our factors are 1, -2, and 3.
Nice. Sounds good. So we're going to work it out algebraically, and we'll test to see if what you got is right there.
On a test, can I just do it on my calculator and then just say p or -3 equals 0?
For the first part, definitely you can just punch it. You need to write down what you did, but then you can say like p of 2 equals this, and then you can punch in your calculator to get the final answer.
Oh.
And then you can say, yes, that is a factor.
Here I
Okay.
just did p equals and then in brackets what I tested.
Yep. So I think you guys have space on your page. We're going to do it two different ways. We're going to learn how to do synthetic division. Okay. So we're going to do long division first, or at least part of it. Maybe I'll set it up and then I won't finish it. So method 1 is long division. I don't want it written way down there. Method 1, long division, and method 2 is synthetic division. So back in grade 5, you learned long division, but you also learned how to shorten it, a little bit of a cheat, and this actually works very similar to that. If you don't remember that, that's okay. But here we go. We're going to set this thing up for long division. So we have our polynomial p of x, which in descending powers of x, with all the placeholders needed. In this case, you don't need any. X cubed plus 2x squared minus 5x minus 6. And we know that x minus 2 is a factor, so we're going to divide it by that. Okay? And you know how this goes, right? You divide the x cubed term by x, you end up with x squared. You multiply it down, you end up with x cubed minus 2x squared. You subtract that out, you end up with 4x squared. You bring down this guy, okay? I'm not going to finish it out. Instead, we're going to move over to synthetic division, and I'm going to teach you how to do that. So the key to synthetic division is setting it up properly, okay? We're going to set up what's called a division chart, and in order to do that, we just need to know the coefficients of p of x.
Is this like Japanese division?
I'm sure they use it other countries, but no, I don't know who developed it specifically. But this is what your division chart looks like. Maybe you want to just watch, and then I'll give you some space to copy it down in a second. But basically, all we're going to do first on this side right here, you essentially have your two rows. You got a row here, you have an answer coming in here, you have a side over here, and you have this top row. That's where we're going to write the coefficients of our dividend of p of x. So it is x cubed, so the first coefficient is 1, plus 2x squared, so the second coefficient is 2. The third coefficient is negative 5, and the constant is negative 6. Notice I left myself quite a bit of space in between, just so I'd have space to show you what we're doing. Now, the factor that we're dividing by is x minus 2. So what I do here over on the left is we're just going to write negative 2. All right? So essentially we have taken the factors of x out of the situation, and we can do that because look at what happens in the long division side to all of those factors of x. We started with a cubic, and we're going to end up with a quadratic. So if we divide out a factor of x from this term, we end up with x squared. If we divide out a factor of x from our x squared term, we end up with something x. If we divide out our x from our x term, we end up with just a constant. So that's going to be assumed when we get to the answer. We're just going to plug our powers of x back in where we know that they go intuitively. The last thing we need, second last thing we need to add to our chart is two things. We need to add a multiplication symbol there. Okay, that's going to relate directly to the idea of multiplying back down. Just like we do here in long division, we go x squared times x gets us x cubed. X squared times negative 2 gets us negative 2x squared. Okay, that's represented there. And then what do? The next step, we subtract. So that step is also in our chart. Okay, so once we have it set up, now we need to simply memorize the steps to synthetic division. The first step, and I'm going to use arrows in different colors and all that, is to simply bring down your first coefficient. Okay? You bring down your first coefficient. What is that the same as? Well, that's the same as saying that the coefficient in front of this term is 1, and I'm dividing it by a binomial that has a leading coefficient of 1. So my result is going to be the leading term is going to have a coefficient of 1. Yeah? If I had a 2 here, for example, and I was dividing by x minus 2, then this leading coefficient would have a 2. It would be the same. Okay? So that's what's happening here when we bring down our leading coefficient. Now the next thing that we're going to do, same as we do up here, the next thing that we do is going to be multiply down. So over here it looks like this. We take this 1. Oh. Nope. I'm going to switch markers here. He's not going to work. What we're going to do is we are going to multiply our negative 2 by 1. So this multiplication sign is helping us understand that we're going to take this 1 and we're going to bring it back into here, we're going to multiply it by negative 2. Okay? So here we go. So we've got negative 2 times 1 is negative 2. Now what do? Well, now we're just subtracting. Okay? So in order to subtract, all we're going to do is go 2 minus negative 1. Sorry, 2 minus negative 2. That's 2 plus 2. That's 4. Okay? And then we're going to
times negative 2.
Negative 4, sorry, positive 4 times negative 2 is negative 8. Now we go negative 5 minus negative 8. That's negative 5 plus 8. That's 3. Now we have negative 2 times 3. Brings us into this box. And we get what we would expect to get. We get negative 6, which when we subtract it, we end up with a remainder of 0. Okay? I'm going to write down the steps of what we did. Okay? We're going to redo it. We're not going to redo it, but we're going to look at what we did and we're going to write down the steps. So once you have it all set up, that's my black marker. That's the grid set up, the synthetic division chart. Then what you're going to do is bring down first coefficient. Bring down the first coefficient. Okay, and we said that's because if you have a coefficient here and you divide it by 1, you're going to get the same number here. Okay, as part of the answer. Bring down the first coefficient. Then we're going to multiply negative 2. That's the negative 2 that's in the top left by the 1. That's the 1 that we brought down. We're going to write negative 2 in the second row. Okay, I'm going to call this the top row. I'm going to call this the second row. Okay. Next, we perform the subtraction. Okay, so the next thing is subtract negative 2 from 2 to get positive 4. And we write that in the bottom. You can see that there. And then we're going to do the same thing. Multiply negative 2. That's the negative 2 from the top left. By 4 to get negative 8. We wrote that in the middle row. You can see that indicated by the arrows, by the blue arrow pointing to the negative 8. And then we're just going to continue. Okay? Dot, dot, dot. Continue. If you can do that, you can do it again, right? Negative 5 minus negative 8, 3. Multiply by negative 2, negative 6. Subtract 0. Okay? Now is the next part that we need to kind of pay attention to and understand. So, we're only dealing with coefficients here. We start with the coefficients of p of x. We divide it all out, and we end up with new coefficients. We end up with the coefficients 1, 4, and 3 are the coefficients of the quotient. The quotient being the answer to a division problem. So 1, 4, and 3 are the coefficients of the quotient. And we know that the factors of x, that the multiples of x rather, are going to be x squared, x, and x to the power of 0, which would be your constant. So the quotient is x squared plus 4x plus 3, and the remainder is 0. What if we didn't get 0 as the remainder? What would that tell us?
That it's not a factor.
That x minus 2 isn't actually a factor. Okay, but we knew we were going to get 0. We already confirmed that x minus 2 is a factor because we tested p of 2 in our original function. Okay, so this is synthetic division. What's the key? Set it up properly. Follow the steps carefully. What does it tell you? It tells you the coefficients of the quotient and the remainder of the quotient. Okay. How do you know the powers of x? Well, the powers of x are all going to drop by 1. Is it possible to get a 0 somewhere in here? Yeah, it just means that that power of x divides out completely and it won't exist in the quotient. Right? If you had x squared plus 0x plus 3, you would drop that middle term completely. It just wouldn't be there, which is fine. Okay? Again, looks a little tricky. Once we do it a few times, you really get the hang of it and you can go a bit. Okay, in example 3, we're asked to combine the factor theorem, which is the strategy we just applied, and factoring by grouping. What that means is we're basically going to use the factor theorem to suck out one factor. Then we're going to use division to find out what's left. And then we're going to use factor by grouping in order to finish out the factorization. So we're given this polynomial expression, and we are going to change that into a polynomial function simply by calling it p of x and say p of x equals x to the power of 4 plus 3x cubed minus 7x squared minus 27x minus 18. And we're going to use the integral 0 theorem. Use integral 0 theorem to determine test values for x equals b. And we know that those come from the constant here, negative 18. So the factors of negative 18 are the ones that we should test. So we're going to test plus or minus 1 is an option, plus or minus 2 is an option, 3 times 6 is 18, and 18 does not divide by 4, it doesn't divide by 5, so I'm on the other side of the hill. If you're thinking about your factors as going up the hill, down the hill, so now I'm at plus or minus 6, and then I'm at the match for 2, which is plus or minus 9, and the match for 1 is plus or minus 18.
But do you have to do factors?
Okay, so the only thing here we have to consider is the constant. I'm going to test a couple of these values. Let's test p of 1. I'm not going to actually sub it in and do the work, but I figure out that this does not equal 0. Okay, so it doesn't give us one of the factors, so I move on. I'm going to try p of negative 1. Turns out p of negative 1 does equal 0. So I'm just going to make a note, therefore x plus 1 is a factor. Okay, now that I have one of the factors, I can use my synthetic division to determine the remaining quotient, what this looks like after it's factored out. And I'm actually going to do that here because we've only seen it once. So let's do that again quickly so that you can see it. Again, I make my chart. X plus 1 is the factor, so I'm putting positive 1 up at the top. I've got a subtraction sign and a multiplication sign. And then I'm simply taking the coefficients of p of x, which are 1, 3, -7, -27, -18. And I'm going to work through this fairly quickly so we can carry on here. But what we end up with, we bring down our 1. Okay, we bring down our 1. That's going to be the leading coefficient of what remains. Then we multiply 1 times 1 is 1, 3 minus 1 is 2, 1 times 2 is 2, -7 minus 2 is -9, 1 times -9 is -9, -27 plus 9 is -18.
No, it's just 8. Oh, yeah.
Multiply by 1 gets us -18, and if I've done it right, I'll get a 0 at the end. That's our remainder. So what have we discovered? We've discovered that p of x is equal to our factor that we divided by, which was x plus 1, times whatever's left here. And all I have is the coefficients, but I know that the powers of x are going to get dumped down by 1. So I'm looking at a first term of x cubed plus 2x squared minus 9x minus 18. And I know it's true because there's a remainder of 0. All right, so now we could use this method a second time on our factor, our cubic factor right here. Okay, so we have -18 again, which means we could use the method to find values of b to test, just like we did up here. Okay, so we could test b equals plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Not 4, sorry. Plus or minus 6, plus or minus 9, plus or minus 18. And then just work with this and bring that factor down, as long as we're trying to say we're equal to p of x, which is up here. The other method that you can use, if you see that something here looks good, looks helpful, okay, you can use factor by grouping, okay? So I'm going to say method 1, which I'm not going to do. Method 1, repeat application of integral 0 theorem on cubic factor, which you know how to do because we've done it a couple times now. Or you could do method 2, factor by grouping. All right, I said use factor by grouping when it looks easier. Well, how do you know what to look for? You're looking at this cubic and you're looking at the coefficients, and I can see that out of here, if I factored out something, I can leave myself with x plus 2. And here I can see the same thing, that -9 and -18 are related in the same way that 1 and 2 are related. Okay, so if I know there's something I can factor out here. If I factor out -9, I'm going to be left with x plus 2. If I'm left with x plus 2 out of these guys and x plus 2 out of those guys, I can factor that out and complete my factor by grouping. Okay, here's what it looks like. Basically, all I need to do is look at the cubic that we have left, which is x cubed plus 2x squared minus 9x minus 18. I'm going to look at this as a group and this as a group. Out of these two, I can factor out x squared, which is going to leave me with, if I factor out the x squared from x cubed, I'm left with a factor of x. If I factor it out of 2x squared, then it leaves me with a factor of 2. Okay, I can double check that thinking by saying, does this multiply back to here. Yes, it does. Continue. Out of this next group, I'm going to factor out negative 9. Negative 9 pulled out of this term leaves me with an x. Negative 9 pulled out of negative 18 leaves you with positive 2. Now I have two terms. What do I mean by that? Well, a term is anything that's connected by multiplication, and a polynomial is a chain of terms connected through addition and subtraction. So I have one term here and one term here. And I notice that in those terms, both of them have a factor of x plus 2. This one is x plus 2 times negative 9. This one is x plus 2 times x squared. So what I can do is I can factor out x plus 2 from the first term. That leaves me with a factor of x squared. And from the second term, that leaves me with a factor of x minus 9. Okay, we're almost there. It looks like we have two factors, but really we still have a quadratic here. So we need to factor this guy even further. Can you see anything familiar?
Sum and product.
Yeah,
Squares.
yes, it's a difference of squares, which factors into the product of a sum and a difference. So we can copy down this x plus 2, and x squared minus 9 factors out into x plus 3, x minus 3. Okay, don't be tempted to say, oh, sweet, I'm done. Okay, you weren't asked in the question to factor a cubic. You were asked to factor the quartic p of x. So your final answer needs to indicate what p of x actually
So
equals.
x plus 1 that we left behind, we can add. We left behind x plus 1. So.
Right, so we left behind x plus 1, yep. So we're gonna make sure we don't forget about him. We're gonna take him down. So p of x, I'm gonna copy down the original, equals x to the power of 4 plus x to the power of 3 minus 7x squared minus 27x minus 18. And in factored form, that equals, and go there first. Take that one first, okay? Take your x plus 1, and now take the rest that you have down here at the bottom. Times x plus 2, times x plus 3, times x minus 3. Now that is fully factored, which is helpful. Why?
We have all our roots?
We have all our roots.
Or all our zeros?
Could you draw this?
Kind of.
You'd have a decent idea of what it would do.
You'd get
Okay.
the right positives and negatives, but not the right ratios.
Right, you wouldn't necessarily know where the local max and mins are, but you'd have a good idea of positivity and negativity.
And we know that
And
all the roots are first degree.
And all the roots are first degree. Yep. Order 1. Definitely. Good stuff. Okay, hopefully you have a little bit of space either right above example 4, probably not, or possibly at the bottom of 12. But regardless of where you write it, you need to take this quick note on the rational zero theorem. It works the same way as the integral zero theorem, but this time p of x has integer coefficients. So, but the leading coefficient is not necessarily 1, okay? This time, x equals b over a is a 0 of any given polynomial where a and b are integers. So that's how you make a fraction. You put an integer over another integer. Where a and b are integers, and the other common restriction, the denominator, a, cannot be 0. Okay?
A is literally never 0 though. So.
Right, because then it wouldn't, yeah, for sure. Okay, because then it would be a totally different polynomial. It would have 1 degree less. So that term wouldn't be gone. What is true here? B is a factor of the constant of p of x. We already knew that. The new thing here is that a is a factor of the leading coefficient.
Wait, it's not the leading coefficient?
Nope, it's a factor of the leading coefficient of p of x. Okay, so of your first polynomial, the coefficient of your binomial that divides it is a factor of that, which makes sense, okay, because it's going to multiply back in the end. And what's your last little thing that we need to know? If b over a is a 0, then ax minus b is a factor of p of x. So if you get the right factor of the constant for b, and you get the right factor of the leading coefficient for a, then you know ax minus b is a factor. Okay, we're going to quick look at example 4 to apply this. Thanks for sticking with me here. Example 4, we're given the forms used to make large rectangular blocks of ice come in different dimensions, such that the volume V can be modeled by V of x equals 3x cubed plus 2x squared minus 7x plus 2. And our goal is to factor this out, so we want to determine the possible dimensions. So we're going to determine the test values, okay? So test values for b are the factors of the constant, okay? So they're factors of 2. So they're only plus or minus 1, plus or minus 2. The test values for a are the factors of the leading coefficient. It's plus or minus 1, plus or minus 3. It's the only things that it can be. So what we're doing is we're finding possible values for b over a, because that's what we're going to test. We're going to see if we can find which b over a is a 0 of p of x, and then that's going to tell us that this is a factor. Okay, so the possible values for b of a, stick with me, b can be 1 and a could be 1, so that would be 1 over 1, and it could be positive or negative, or you could have 1 over 3, positive or negative. So I'm just going to write those, but I'm going to try to write them in order as I do it. So we've got 1 over 3, could be positive or negative, 1/3. Okay, you have 1 over 1, which is positive or negative 1. Then with this value, the factor of 2, you have 2 over 1 and 2 over 3, and they can both be positive or negative. 2 over 1 is just 2. 2 over 3 is 2/3. Okay, there's our possible values. Those are the only values that you have to test. And if you determine that the value of the function v of x, when x is one of these, then you have found the 0. Okay, I'm going to do that just for a quick second. What are we going to do? We're going to try the easiest one first, which is a value of 1. So I'm going to try to find out the value of the function at 1. And look, 3 plus 2 plus 2 is 7, and minus 7. Okay, so we found out that that one is 0. Therefore, x minus 1 is a factor. So we didn't even do one of the harder ones. We didn't even do 2/3 or 1/3. That would be good to practice. Still, we're not going to do it. You could test them all. We could do, I'm going to do one more. I'm going to do p of 1/3. Okay, if you put 1/3 in here for x, you also end up getting 0. You can trust me on that one. What does that tell us? Well, look at it, b over a. So that tells us a is 3 and b is 1. That tells us 3x minus 1 is a factor. Okay, once you had one factor, you could have used a different method. You could have divided this out.
Well, where'd you get 3x from?
So because 1/3, a is 3,
Oh, okay.
and b is 1. And here's your base, ax minus b. Okay, so we haven't factored this thing out fully, but we found 2 of the factors. There's going to be one more factor because we're dealing with a cubic. And in order to do that, you could just divide it by both of these, or you could continue doing this method. If you did, you would find out that the last one is negative 2 gets you a value of 0. So x plus 2 is a factor. That's the 3 factors. Okay, your practice problems are from page 102, numbers 2 through 7 and 9 through 11. Thanks very much.